If you recall, one of the very first lectures we had in calculus was talking about the two branches of calculus, differential calculus, which we've looked at quite extensively, and now we're going to start looking at the second branch of calculus, integral calculus. The study of integral calculus starts with the idea of antiderivatives. Integration is a technique that we use to find areas underneath curves for one definition, and it's also another technique that we can use is to find antiderivatives, meaning we try and find the function where a derivative came from. So instead of being given the original function and asked to find the derivative, we're being given the derivative and asked to find the original function. This is also takes place in differential equations, and you guys will take most of you will take an entire semester of differential equations. So we'll touch on that topic here, but not as extensively as you will when you take the entire course. Now, just like addition, the inverse of addition is subtraction, the inverse of multiplication is division, the inverse of differentiation is integration. Integration and antidifferentiation are essentially the same thing, but with integration what we end up doing is we have a pattern or an algorithm that helps us solve integral problems. Whereas with antidifferentiation, we can see patterns, and when we start to see some of these patterns develop, we can kind of guess at that original function. To show what this means, let's go ahead and look at an example. Suppose we know the first derivative is equal to 2x. This is the question then. What is our original function? What did we take the derivative of to get 2x? Well, by inspection we can see pretty easily that that original function must have been x squared. Well, but it could have also been x squared plus 2, because if we take the derivative of x squared plus 2, the derivative of x squared is 2x, the derivative of 2 is 0, so that would work. Well, the f of x equals x squared minus 7 would also work, because the derivative of a constant is 0. So another solution would be f of x is equal to x squared, let's say, minus 100. That would work as well. So a lot of times what we end up doing, instead of writing out all these different constants, we can say, you know what, the original function was equal to x squared plus some constant. Now this constant could have been positive or negative, so I don't need to worry about whether I say plus c or minus c, because again the constant could have been positive or negative. Now there's a lot of very interesting characteristics that are coming out of this. If I were to graph each one of these, they would all look the same. They would all be a parallel function. For instance, this would be the graph of x squared plus 0, which would be an antiderivative. We could have the graph of x squared plus 2. We could have the graph of x squared minus 7. And the graph of x squared minus 100, I don't want to scale this, but here would be x squared minus 100. So you can see that all these graphs are parallel. They are just the same graph, just shifted. Now these down here ended up looking a little bit wider, but in reality they wouldn't. They are all from the same family. So instead of looking at a solution, what ends up happening is we get an entire family of antiderivatives as my solution. So this tells us that the antiderivative is not unique. And because the antiderivative is not unique, we can get more than one solution. And this plus c, this constant, which we'll eventually call the constant of integration, basically represents all those possible solutions. Now we need to look at a specific note on notation here. So this notation change involves using a cap f and a lowercase f. So specifically, we have a function cap f of x. Cap f of x is known as the antiderivative of our lowercase f of x. On the open interval ab, that means it has to be differentiable, if the first derivative of cap f of x is equal to lowercase f of x. And this has to be true for all x in the interval, open interval ab. Now this is a little bit confusing, so to clarify this, let's go ahead and look at a few examples. But there is a difference when you see in your textbook a difference between the cap f of x and the lowercase f of x. So for this example, let's go ahead and look at a cap f of x equal to x squared plus 2. Now cap f of x again is the antiderivative. Actually, it's one of the antiderivatives, because remember, antiderivatives often will produce an entire family of values unless I'm given some initial condition. So cap f of x is equal to x squared plus 2. This is an antiderivative of the lowercase f of x function 2x. So if I look at f of x, lowercase f of x, and I think, where did this derivative come from? Because f of x is the derivative. That could have come from x squared plus 2. It could have come from x squared plus 3, x squared minus 7, etc. Now this works because cap f prime of x is equal to the derivative with respect to x of x squared plus 2. So this is just notation. Cap f prime of x means the derivative with respect to x of this function. So that's all we're doing. We're not solving for anything here, we're just kind of rewriting it. Well, the derivative of x squared plus 2 is 2x. The derivative of 2 is 0, so that's 2x, and this is equal to lowercase f of x. So don't get confused here. It's easy to get confused because of the notation. You're looking at this and you're thinking, this should be my f prime because this is my derivative, and this is my original function. But what this is saying is my original function is cap f. My derivative of my original function, f prime of x, is equal to 2x, which we denote lowercase f. So the antiderivative is cap f, the derivative is lowercase f. Now, don't worry about this too much because it does get a little bit confusing, but we'll see this notation often enough that it will become second nature to work with. Let's go ahead and look at another example involving a trig function. In this case, cap f of x is equal to the tangent of x. This is an antiderivative of lowercase f of x, and let's think about this. What did I take the derivative of to get back here? So in other words, the derivative of tangent is secant squared. So therefore the antiderivative of secant squared is tangent. So that works pretty slick. In fact, we'll have to make a chart here and memorize these. So this works because the derivative of cap f of x, which is just the derivative of tangent of x, is equal to secant squared of x, which is denoted lowercase f of x. Now we're going to learn a new symbol. This is the integral symbol. And in order to talk about antiderivatives or antidifferentiation, we use this symbol called the integral. The integral of lowercase f of x dx is equal to the cap f of x plus c. Now, we can always check our integral answers. If we take the derivative of our solution, so if we take the derivative of the right-hand side here, I should get the argument of my integral back, and that's called your integrand. So the derivative of cap f of x should just be my integrand, or lowercase f of x back. And this is a checkpoint that we're going to use a lot. Let's go ahead and talk about what each of these pieces are. Lowercase f of x is called the integrand. Dx is called your differential. And we'll learn a little bit more about where these come from in the next chapter. Cap f of x plus c is called the general antiderivative of f of x. Now there's one other piece here. This plus c is included in this definition, and then plus c also has another definition standing by itself. It's called the constant of integration. So if you integrate, we always have to include this to acknowledge that there's an entire family of solutions for this antiderivative. Now sometimes we have limits of integration, which we'll get into in another chapter as well, and then I don't have that constant of integration because I have conditions where I can actually find what that plus c would be. Let's go ahead and look at an example using this integral notation. So for this example, I want to look at the integral of the sine of x dx. So I know I'm going to get something plus c. Now let's think about this a little bit backward. I really don't know anything about the integral of the sine, but I do know that if I take the derivative of cosine, I get negative sine. So therefore the integral of sine must be negative cosine. So to check this, and remember you can always check all of these, you take the derivative of your entire family of integrals that you have on the right, and I better get my integrand back. Well, what's the derivative of a negative cosine? Well, we drag along the minus sign. The derivative of cosine is a negative sine of x. The derivative of c is 0. Minus a negative is the same as a positive, and I get sine of x here. And this does check because that was my original integrand. So again, you need to think about these backwards. You know the derivative of cosine is negative sine. Therefore, the integral of sine is negative cosine. So let's go ahead and make a list of these antiderivatives that we can learn just from knowing our trig functions. So these would be basic trig antiderivatives. Now we will not have an integral for something like tangent yet, not till Calc 2. We won't have anything for cotangent, the integral of cotangent. We won't have anything for the integral of secant, because I need other types of functions to be able to work with these called natural log functions, which I'm sure you've looked at before. So for now, we can only take our antiderivatives. So we already know that the integral of sine of x dx is equal to the negative cosine of x plus c. So let's go ahead and make the rest of the chart. Okay, looking at the rest of our chart here, we're just taking the antiderivatives, meaning if we know the derivative of sine is cosine, we know the integral of cosine is sine then. The derivative of tangent is secant squared, therefore the integral of secant squared is tangent. Now with these we need to worry about the negative sign. The derivative of cotangent is negative cosecant squared, therefore the integral of cosecant squared will be a negative cotangent. The derivative of secant of x is secant of x tangent of x, therefore the integral of secant of x tangent of x is equal to secant. And our last one here, the integral, or sorry, let's start with the derivative. The derivative of cosecant of x is negative cosecant x cotangent x, therefore the integral of cosecant x cotangent x is negative cosecant x. Now everything that we've looked at here, the arguments are all just basically x, but that's not always going to be the case. So for right now, all of our trig functions are just some trig function of x, trig of x, like sine of x, cosine of x, tangent of x, etc. Pretty soon we'll start changing that argument to not only just be x, but like 3x, maybe even x squared or x cubed, depending on what level of calculus you're at. So again, right now we don't know the integral of tangent, we don't know the integral of secant, we don't know the integral of cotangent. So we don't know the integrals of all of our basic trig functions, but these are the ones that we know based on the fact that we know derivatives. So you will definitely want to have these memorized. We're going to use these so often over the next few years that it will be very helpful to have those memorized. Let's go ahead and look now at the power rule for integration. The power rule for integration uses the same concept as the derivative, but it inverses it. Now remember, with the derivative you brought the exponent down and then decreased it by 1. Well, what we're going to do with the power rule for integration is we're going to increase the exponent, and then instead of multiply we'll divide by that new sum. So let's go ahead and look at the integral of x to the n dx. So notice my base is my variable here, n is my exponent. This differential x relates to the variable that we have here. With the power rule for integrals, and again it's just the inverse of taking a derivative, you add 1 and then divide by that sum, and then add your constant of integration. Now a couple of things have to be careful about here. N cannot equal negative 1. And you might say, well, why can't n equal negative 1? Well, if we had n equal to negative 1, I'd have x to the negative 1 dx, which is the integral of 1 over x dx, if you want to think of it that way. Or from this way, when we add 1 and divide by the sum, I get x to the 0, which is fine, but divided by 0 is not fine. This is undefined. And in Calc 2 we'll learn that the integral of 1 over x dx, or x to the negative 1 dx, is the natural log of x, but we're not looking at natural log functions yet. So if we run across the case x to the negative 1, we can't integrate that right now. Now we also have a few other rules about integrals. If I look at the integral of some f of x plus or minus g of x, meaning I have two functions like x plus x squared, what I can do is I can just take the integral of each piece. Now usually we won't do this because it's handier just to kind of look at them together, but the first couple of examples I will split those up. The next rule that we want to look at is a constant multiplier rule. So if we have some constant times a function that we're trying to integrate, what I can do is I can just pull that constant out front and then just integrate the function that's left behind. There are another few rules. They don't bring them up right now in this section, but I'm going to bring them up because they're very important. What if we had the integral of a product? The integral of this product does not equal the integral of each individual product. So the integral of the product does not equal the product of the integrals. So this is not true. But I'll tell you, a lot of people try this just because they don't know what else to do, so they try and just separate the functions out. Now this is also true with a quotient. The integral of a quotient does not equal the quotient of the integrals. So this is not true ever, 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 ever. So these two rules, avoid these. Do not make these mistakes. So let's go ahead and look at an example then where I can start applying these rules. Now for the first couple sections that we work on with these integration techniques, I would write out each step if I were you, just so you get used to the steps and then you get used to the rules, and then pretty soon you can start shortcutting. But if you start shortcutting right away, then clearly errors can start to arise. So let's go ahead and look at the function 4x cubed minus 2x to the 3/5 plus 1 over x squared, and then let's do a minus 1 dx. Now this particular integrand basically covers all of our rules that we have up till now. This integral is the integral of a sum and a difference of functions. So if I wanted to, what I can do is I can split this up into separate integrals. So this 4x cubed, I could also pull the 4 out front. 4 integral x cubed dx minus 2 integral x to the 3/5 dx plus the integral of 1 over x squared dx minus the integral of 1 dx. So I can follow that rule that I had right up here that said the integral of a sum is the sum of the integrals, or the integral of a difference is the difference of the integrals. And then I use this constant multiplier rule with that first integrand 4, and I pulled it out front. Okay, so now I can probably start taking an integral of each one. Oh, except this one. I'm going to have to rewrite that one. Now you might look at that and think, well, I don't need to rewrite it. I can just integrate it where it's at in the denominator, and I actually can't. I need to rewrite this flipped up top. So this looks like the form x to the n. Each of these looks like the form x to the n, x to the n, x to the n. Now this last one we could probably rewrite a little bit too, just to clarify. There is no x on this last one, so if I wanted to I could rewrite it as x to the 0. Now pretty soon when you see the integral of a constant you're going to know exactly what to do. But for now, let's go ahead and show why the integral of a constant turns out to just be the variable times the constant. So starting along, I drag the 4 along. Now remember my power rule that I want to use here is to add 1, so I have 3 plus 1 divided by 3 plus 1. So 3 plus 1 is my exponent, it's also my denominator. Minus 2, x to the 3/5 plus 1, but 1 in this case I'm going to rewrite as 5/5 because that'll allow me to add my fractions easier. Here, actually I'm going to integrate this so I can drop my integral sign, and that's an important point. Once you integrate, you drop the integral sign. It's kind of like once you multiply 2 times 6, the multiplication symbol, the times symbol is gone. So from here, I will add 1, so I get negative 2 plus 1 divided by the sum negative 2 plus 1. Now this is kind of our more interesting one. I drag the 1 along, and then I add 1 to my exponent, and then I divide by the sum. And then each of these technically has a plus c, plus c, plus c, plus c. But what we do is we don't consider the constants for each of these. What we do, instead of including them on each of the smaller integrals, we include one large constant at the end. And I don't mean large in size, I mean large in the fact that I take all these plus c's and combine them to equal a larger value of plus c. So again, I don't talk about a plus c, a plus constant of integration for each of these, I just include one in the end. And of course we're going to want to simplify the heck out of this. So we have 4 x to the 4th over 4 minus 2 x to the 8/5, 3/5 plus 5/5 is 8/5, divided by 8/5, plus x to the negative 1 divided by negative 1. And then this is the interesting one. X to the 0 plus 1 is x to the 1st divided by 1. So what ends up happening here is when I have the integral of a constant, I just get whatever the constant is times x. And of course I have my plus c, my constant of integration. Well, the 4's cancel here, so that makes it a little bit easier to write. So rewriting, I end up with an x to the 4th minus 2. Now when you divide by 8/5, that's the same as multiplying through by 5/8, x to the 8/5. Now here, I don't want to leave this negative exponent, so I'm going to flip it. So x to the negative 1 becomes 1 over x, and then this minus sign pops out front. And then over here, you know, you're not going to cancel the 1's because you just get 1 anyway. So minus x plus c. And it looks like we can do a little simplifying here. 2 goes into 8 4 times. So I end up with x to the 4th minus 5/4 x to the 8/5 minus 1 over x minus x plus c. This is your antiderivative. This is the entire family of antiderivatives, represented the family part by plus c because I can have any constant here. Now how on earth could we know if this is right? Well, first of all, Maple does these very easily. Okay, but sometimes they simplify funny. But one way we can know how if this is right is to check it by taking the derivative of the original function. So we take the derivative of, not the derivative of the original function, we take the derivative of the solution. And then what we hope is the derivative of the solution will equal our integrand that we started with. So the derivative of x to the 4th is 4x cubed. The derivative of negative 5/4 x to the 5th, I drag along the negative 5/4, I bring the 8/5 down, and then I decrease this exponent by 1. 8/5 minus 5/5 is 3/5. Okay, now the derivative of minus 1 over x, I can think of this as minus x to the minus 1. I bring the negative 1 down. A negative times a negative is a positive x to the negative 2. And the derivative of a negative x is a negative 1, and the derivative of a constant is 0. So let's see if we can rewrite this and get this to match. 4x cubed minus 4/8 is the same as 2x to the 3/5 plus 1x to the negative 2 is 1 over x squared minus 1. So this is what we're trying to check to see if this is right. So let's go look at our original and see if it matches. So here was our original, 4x cubed minus 2x to the 3/5 plus 1 over x squared minus 1. And it does match. So it matches, so this checks. So that means this is the right answer. Okay, let's go ahead and look at Maple and see how we can integrate or find antiderivatives in Maple. First of all, under your expressions tab here on the left, there's an integral sign. And right now we have indefinite integrals, so this is the one we would choose. We'll use this one a little bit later for definite integrals, but for now we could choose this one. Or as you can see over here, you can type in the int as an integral command. This stands for the function that we want to integrate, and then x has to do with that differential, dx, because sometimes I could have more than one variable that we're looking at here. Well, for this example I used 4x cubed, and again you have to put in the asterisk for multiplication. 4x cubed minus 2 times x to the 3/5, I believe. Okay, and I think it's a good idea to put the 3/5 in parentheses so Maple understands that not just the 3 is your exponent. Okay, plus 1 over x squared. And I'll put the x squared in parentheses as well. If you wanted to rewrite that as plus x to the negative 2, you could as well. And then I believe we had minus 1. So hit enter, make sure you have your semicolon. Oh, and it doesn't like what I have here. If you notice, it just rewrote the original function and I have a cap x here, so I need to go up and fix that. Let's make this a lowercase. Must have my cap locks on, lowercase, and see. Okay, so there's my integral, x to the 4th minus 5x to the 4th minus 5/4 x to the 8/5 minus 1 over x minus x. So let's go ahead and bring that into Journal and see if that compares with what we had. It does not put the constant of integration on for us. but you can see x to the fourth minus 5/4 x to the fifth minus 1 over x minus x. So we need to remember the constant of integration. Maple will not do that for us. Some of the most interesting problems that we can be working in integration is to actually work problems that have initial conditions, where we can actually find the value of c. And so when we talk about these initial conditions, we're actually going to be talking about solving differential equations, and that's really neat stuff. So let's go ahead and look at some initial condition type problems. So an initial condition basically tells or specifies a single function or graph. Remember that entire family of graphs that we had. From that entire family of graphs as the antiderivative that is the correct solution given a set of particular conditions. And usually they're called like initial conditions in physics, but they don't necessarily always have to be initial conditions. An antiderivative, like the ones that we're going to be working with, so an antiderivative is actually a solution, as I said before, to the differential equations diff(eq) dy dx equals lowercase f of x. So this means the derivative of this function y with respect to x is equal to the lowercase f of x. So that's what we're going to be basically doing, is solving these types of differential equations. So let's go ahead and look at some basic examples to get started with here. The first example, let's go ahead and look at dy dx, meaning the derivative is equal to 2x to the 8th. And I would like to find the solution that is subject to the initial condition and the initial condition that we want to work with is y of 0 equals 1. So to solve for this differential equation, because this is a differential equation the way it's written, I'm going to multiply both sides through by x, and I get dy equals 2x to the 8th dx. And then what I'll do is integrate both sides. The integral of dy is equal to the integral of 2x to the 8th dx. Now integration is kind of new for us, so we'll go through this step by step. This is an implied 1 dy. And remember, when you integrate a constant, you get the constant times the variable. The variable in this case is not x, it's y. So basically I have y equals. That's what I have on the left. Now over here on the right, when I integrate, remember we add 1, so I'm going to get 2x to the 9th, divide by that sum over 9, plus c, my constant of integration. So this is our initial solution. This is our general solution because I have this plus c, this constant of integration. Now what I want to do is I want to apply our initial condition. So our initial condition was y of 0 equals 1. Y of 0 equals 1. So this means y is equal to 1. And this 0 means everywhere there's an x, because that's my other variable, in my function, I replace it with a 0. So this looks like 1 equals 2 times 0 to the 9th over 9 plus c. Well, what we can do here is get 1 equals 0 plus c, or 1 equals c. So I have solved using my initial condition, and now I know that my antiderivative that's correct for this initial condition is y equals 2x to the 9th over 9 plus 1. This is called a particular solution. Remember, before we had an entire general solution or an entire family of solutions, but now we have this nice particular solution. Let's go ahead and look at another one that involves a trig function. Okay, so this example we're going to be looking at dy dx equals cosine of x with the initial condition y of pi over 2 equals 3. So the first thing that we do is we solve for dy. So we have dy equals cosine of x dx. Then I integrate both sides. And always put parentheses around the arguments of your trig functions. The integral of dy is y, 1 times y. The integral of cosine is not negative sine, because the derivative of cosine is negative sine. The integral of cosine is sine. So we want to think about this as an antiderivative. The derivative of sine is cosine, therefore the integral of cosine is sine, plus c, my constant of integration. Now the initial condition that we're looking for here is y of pi over 2 is equal to 3. So that means that y is equal to 3, and everywhere I see an x, I'll plug in pi over 2. So I end up with 3 equals sine pi over 2 plus c. And of course we know the sine of pi over 2 is 1. Subtract 1 from both sides, I get c equals 2. So the particular solution is y equals sine of x plus 2. This is my particular solution to this differential equation. And I had to use antiderivatives in order to find that. Let's go ahead and look at one last example. And this last example we're going to be looking at position, velocity, and acceleration. You probably recall from our differentiation chapters that s of t is used as the position function. In order to find velocity, I would take the derivative of position. In order to find acceleration, I would take the derivative of velocity, which would be the second derivative of position. So moving down here, I was differentiating. However, now that we know how to find antiderivatives, I can integrate up. So if I am given acceleration, I can integrate acceleration to find velocity. So that's one thing that would work really well here. I can integrate velocity to find my position. So again, we differentiate down this column and we integrate up this column in order to solve for problems. So this last example that we will look at, we'll use this idea of position, velocity, and acceleration and kind of move it from differentiating to integrating up. So for this example, we're looking at a particle that's located at the origin, so it's starting its travels at the origin at time equals 0. It moves in a straight line and it has an acceleration function a of t equals 4 minus 1/2 t, which is linear as well, feet per second squared. As usual, let velocity v of t and s of t be the position function at time t. What we want to do is we want to first of all state and solve the differential equation for velocity, assuming the particle is at rest at t equals 0, meaning it's not having a running start, it's starting at rest. Well, this initial condition basically implies that the velocity at 0 then is 0. So the velocity at time 0 is 0. So let's go ahead and start by stating and then solving the differential equation. The differential equation goes back to the derivative of velocity, dv dt, is equal to acceleration. We would solve both sides here for derivative of velocity, dv, and I'd get a of t dt. Then we could integrate both sides, and I have the integral of dv is equal to the integral of a of t dt. Well, we already know what a of t is in this case. The integral of dv is v. The integral of a of t would be the integral of 4 minus 1/2 t dt. So we have velocity equals, the integral of 4 is 4t in this case, because remember the integral of a constant is the constant times the variable of interest, which in this case is t, minus 1/2 t squared over 2. Rewriting velocity equals 4t minus 1/4 t squared plus c, my constant of integration. And I could include that plus c over here as well. So there's my velocity. So I'm going to rewrite this as v of t, because that's my velocity function, is equal to 4t minus 1/4 t squared plus c. Now, the initial condition that I need to apply here then is v of 0, the initial velocity, is equal to 0. So, this notation, 0, I plug in for v of t. And everywhere I see a t then, I'll plug in this value of 0. And then we can solve from there. So what ends up happening is I get v of 0 is equal to 4 times 0 minus 1/4 0 squared plus c. But v of 0, if you'll recall, was 0. So solving here, I just get c equals 0. So this is not a very exciting function. I just get my constant of integration again. So v of t is 4t minus 1/4 t squared, and then plus my value of c. But we just determined that c was 0, so this is my velocity function. Now this velocity function is only true under these initial conditions right here. So this is a particular solution to that differential equation. Part B of this problem, we're going to be looking for the position function. So in determining the position function, they've already given us our information about the initial condition, because at the beginning of the problem it says the particle located at the origin at t equals 0. So our position is 0 at time 0. So our initial condition was not specifically given here, but it was implied in the problem. So that's s of 0 equals 0. Now these initial conditions are pretty easy to work with. Now we can set up a differential equation and solve, where you can kind of start jumping ahead and think, okay, well the position function is going to be equal to the integral of the velocity function with respect to t. And again, that's just from solving your differential equation, the derivative of position over time, ds dt is equal to velocity. And then multiplying both sides through by dt, and then we're looking for integrating ds, which is s of t, or s. So s of t would be the integral of our velocity function. Well, our velocity function is 4t minus 1/4 t squared dt. Now you might say, well, wait a minute, we can't use this because this is only under particular conditions. But let's think about what would happen here. In this case, c equals 0. But if c would have been 12 or negative 24 or negative 36, that would change my velocity function that I have here. And so again, we have to kind of watch out for that. This is only underneath this set of initial conditions. And if you kind of guessed at that, you would be correct. So let's go ahead and integrate. And we have s of t is equal to 4t squared over 2, add 1, divide by the sum, minus 1/4 t cubed over 3 plus c. So s of t equals 2t squared minus 1/12 t cubed. Now the initial conditions that we need to be concerned about here are s of 0 equals 0. So s of 0, as I'm plugging in for here, that's equal to 0. So I have 0 equals. Now this value of 0 means everywhere I see a t, I plug in a 0. 2 times 0 squared minus 1/12, 0 cubed, plus c, forgot my plus c up here, implies that c equals 0. So my position function looks like 2t squared minus 1/12 t cubed plus c. But I just figured out under those initial conditions c is equal to 0. So this is my particular solution to that set of differential equations using that initial conditions. So these types of problems I think are the little bit more interesting ones, using integration and antiderivatives to solve position, velocity, and acceleration type functions, as well as looking at this in terms of initial conditions. In the next chapter we'll actually be getting into Riemann sums and explaining why integration works the way it does, but for now we're just using this idea of antiderivatives. Thank you.